Hello and welcome back to this lecture 34 on biomicroelectromechanical systems. Let us do a quick preview of what we did last time. So we talked about designing and development of electrochemical valves. This was followed by capillary force valves and thermocapillary effect, and we used this effect also to study pumping, micropumping and valving later on. So as you know, capillary force valves are essentially based on electrical fields applied to bubbles with an unequal or non-homogeneous distribution of charge on the surface. Similarly, thermocapillary effect is done by changing the surface tension on both ends by heating a bubble differentially, and the idea is that the bubble moves towards the lower surface tension. Well, the surface energy kind of balances for the bubble to move into that direction. We also talked about micro pumps and then classified them into mechanical and non-mechanical, and this is essentially dependent on the way that energy is being added to the system. You can have energy added by means of vibrating membrane or vibrating boundary, which can be the mechanical micropump, and the non-mechanical basically would include a form of energy added without any vibrating membrane, and energy is directly pumped in by other inducing mechanisms like electric fields, magnetic fields, so on and so forth. We also talked about pumping pressure, head and efficiency. Pumping pressure, as you know, pressure head is basically also found out by looking at the Bernoulli's equation, and efficiency is essentially the actuation efficiency. This basically equal to the flow rate causing. Okay, so therefore the pumping efficiency is also the difference between or the ratios between the power required for pumping divided by power required for actually actuating the micro pump. So essentially power supplied, it is a ratio between the power generated by means of flow and the power supplied into the system. So this is as far as last lecture goes. Now today we will be starting on designing, and we also talked about in the last lecture about one thing which was a kind of phenomena which was related to peristalsis. Peristalsis, as we know, also is a motion of travelling contractile in a microchannel which causes flow to happen, and so therefore we essentially discussed about a 3-layer device wherein actuation is done by means of by mechanical means, by moving boundaries with high pressure compressed air flowing in a sequential manner into the blisters, which causes the movement of the fluid underneath it. And so therefore essentially what happens is that the contractile motion is discretized and which results in a unidirectional flow within the microchip. So today we will be discussing a design problem to begin with, where we talk about how such mechanical pumps can be designed and developed. So therefore in this particular example, as you see, there is a peristaltic pump which has 3 pump chambers and a circular uniform piezo disc, unimorph piezo disc as actuator, and the pump membrane has a diameter of about 4 mm. Okay, and the pump works at a frequency of about 100 hertz, and we need to determine the volume flow rate at back pressure. The maximum membrane deflection is about 40 microns. So here we actually assume that the membrane deflection give me a minute here, so that we actually assume that the membrane deflection follows the deflection function of a thin circular plate. So we assume the diameter or the deflection at radius r from the center is also equal to d max, which is the maximum deflection at the center, minus 1 minus small r by big R square whole square. Essentially small r is the radial distance from the center of a point, and big R is the overall radius of the membrane. Okay. So, using this deflection function, we need to find out what really is the volume displacement at a certain radius r from the center of such a circular unimorph membrane, which is moving and causing the peristalsis effect within the micropump. So, here essentially let us draw this. You have a circular chamber here, and there is a radial distance r over which we are considering the deflection, and so really and also we are assuming that there is a distance dr in this region of the element which we are considering the deflection of. So, essentially if you just draw a circle around this point, of radius r and another circle at radius r plus dr, if you would like to consider the area which is available between this r and r plus dr. So, the area essentially is, if you do it, so if you consider a small angle d phi here between the radius r and r plus dr, and we want to find out really what is the area of cross section or what is the area, total area of this particular element here, which is shaded as you are seeing, it is really given by r d phi times of dr. Okay. So, essentially r d phi being this length sector, and dr is the small elemental distance between the r and r plus dr, the twin radii as we are seeing, and we can assume that this particular section here d phi being very very small represents kind of a rectangle. It is not really having you know an issue of differential distances on both sides. So, you have the opposite sides, the difference between the opposite sides so small in this case that we can safely assume this whole area to be rectangular in nature. The thickness of the rectangle being dr, okay, and the length of the rectangle being r d phi as defined by the length of the arc on this particular side. So, having said that, we can calculate the delta v, the small elemental volume, as this particular element deflects dr, let us say, where dr is a function of r, the deflection. We can calculate the total volume delta v by multiplying this particular area term with the deflection, which is d max times of 1 minus small r by capital R square whole square. Okay. So, that is what the distance dr would be, or the deflection dr would be, times of r d phi dr. And if we want to find out the overall volume in this case, let us say the total volume deflected of the circular component would also be given as phi varies from 0 to 2 pi, radius small r varies from 0 to capital R. You have this as d max times of 1 minus small r by big capital R square whole square r dr d phi, and this essentially comes equal to 2 pi by 3 d max times of square of r, and this is nothing but, as you know, the d max in this case is essentially 40 microns. It has been mentioned in the question that the maximum deflection at the center is 40 10 to the power of minus 6 meters. Radius r has 2 millimeter size because the diameter is 4 mm. So, it is 2 10 to the power minus 3 meters, and therefore, the total volume deflected is essentially equal to 2 pi by 3 times of 2 10 to the power of minus 3 square times of 40 10 to the power of minus 6 meter cube. Okay. And this becomes equal to 3.35 10 to the power of minus 10 meter cube. This is what essentially the total volume deflected then would be. So, at a relatively low frequency, give me a minute here. So, at a relatively low frequency, which is actually 100 hertz in this case, it's relatively very small. We assume that there is a linear relationship between the volume flow rate and the pumping frequency. Okay, so we assume a linear relationship. So, in other words, the pumping rate Q is delta V times of F, which is 3.35 10 to the power of minus 10 times of 100, which is essentially 3.35 10 to the power of minus 8 meter cube per second, which is about 2 ml per minute. That is what essentially the total flow rate in this particular case would be. Okay. Now, we have also talked about thermocapillary effect, and I would like to just do another example with you guys about how this effect gets realized. So, let me just reiterate what thermocapillary would mean. It is also known as Marangoni effect. Essentially, you have a bubble, okay, and a bubble is essentially a two phase. So, you have either a gas bubble inside liquid or an oil bubble inside liquids, some kind of change in the continuum. There are two phases which describes a bubble, or two states which describes a bubble. Now, in this kind of a situation, when you heat the surface of the bubble differentially, with one side heated more in comparison to other, there is a change in surface tension and there is a distribution of surface tension across the bubble. So, the bubble would have a tendency of moving towards the lower surface tension from the higher surface tension. Okay. So, it moves forward in the direction of the lower tension, or in terms of it moves forward in direction of the more heated or more prominently heated side. So, that is essentially what a Marangoni effect or thermocapillary effect would mean. Okay. So, let us actually do an example where we talk about how we can determine the driving force on a bubble given the surface tensions of water air interface, and that too given at different points of temperatures in which the bubble is heated up. Okay. So, let us do this example. On Marangoni effect. So, we have a thermal bubble which is created in a capillary. This capillary has a radius of 50 micrometers. The temperature at the two ends of the bubble are 100 degrees and 50 degrees Celsius respectively. Okay, you have to determine the driving force of the bubble given the surface tension of the water air interface is 58.9 Newton per meter at 100 degrees Celsius and 67.91 Newton per meter at 50 degrees Celsius. Okay. So, let us say we have a pressure difference at two ends of the bubble which is estimated as delta P. So, delta P pressure difference is essentially also defined by twice the surface tension of sigma, also sigma of air water interface at 50 degrees Celsius and that at 100 degrees Celsius. As you know, with the increase in temperature the surface tension decreases. Okay. This per unit hour, this is the standard formula of determining the pressure difference which is existing within a bubble in a certain environment, and delta P is essentially the pressure differential that the bubble can withstand, still becoming one integral with respect to the atmosphere. and that essentially is given by the difference in surface tensions across. So, one side would have definitely more withstanding capability and another would have less withstanding capability, and so essentially the total pressure difference in that case across the surface is basically twice sigma by r, twice delta sigma by r, where delta sigma is the difference between the surface tensions at both temperatures. Okay. So, here both are given, and essentially the area here in this case is nothing but as you know, with the 0 contact angle, the total area available on a line wise basis. So, the total area available at 0 contact angle, when we assume the whole droplet has kind of spread over the surface, is pi r square. Okay. Pi times of square of r, r is the radius of the particular bubble in question. So, the force F is also equal to delta P times of A in that case, which is actually equal to nothing but because you have this area pi r square, you have twice pi r times of sigma at 50 degrees Celsius minus sigma at 100 degrees Celsius respectively, which on calculation comes out to be equal to 0.9 micronewtons. So, as you are seeing here, the force really which is which kind of arises because of this differential surface tension is only about 0.9 micronewtons, about close to 1.0 micronewton, and this is sufficient to move the small mass of the fluid bubble towards the surface which is more properly or more strongly heated up actually. So, that is what the Marangoni effect essentially would do. Let us also study some other forms of micropumps which may be of interest to the readers. But this right here is a very good illustration of a valveless rectification micropump. And what essentially it means is that you have it is all based on again the Bernoulli's principle. As you see, this side here, this end here acts like a diffuser and here acts as a nozzle. So, as you know, if we assume the overall pressure head or the pressure difference between both sides, okay, between this side and this side, which is also given by height delta H is 0, it's or basically the pressures on both sides here are same to each other. Therefore, in that kind of a situation, of course, because of the greater amount of cross sectional area here, the pressure head would be more, okay, and the velocity head would be less. However, in this particular area, as you are seeing, so this is here where the pressure head is more and the velocity head is less. And in fact, on the other end, if you look at really in this particular case, the pressure head is less and the velocity head is more. Okay. So, therefore, there is a differential pressure delta P between these, which causes the fluid to kind of move in this particular direction. Alright. So, it moves all the way from the high pressure zone towards the low pressure zone here. Okay. And so, fluid moves in this direction across the microchannel. Similarly, there can be a situation where the fluid can move in the opposite direction as well, depending on if just you are able to kind of change the geometry here. Also, there can be active valveless rectification systems wherein this particular microchannel area can be further using a peristalsis effect be changed. So, therefore, not only there is a pressure head, but also there is a continuous force here which kind of vibrates the membrane and compresses it. So, that all the fluid which is inside actually goes towards the higher velocity head side or lower pressure head side, because more is the cross sectional area, lesser would be the addition in the velocity component here due to this pumping action. Lesser is the cross sectional area, more would be the addition of the velocity component. So, it acts as kind of an amplifier in the same direction as we considered before, and the pump actually pumps out fluid from the right end towards the left end. So, that is essentially what this valveless rectification pumping systems do. Okay. Now, there are other forms of pumping systems, one of them being rotary pumps with spur gears, as you can see here in this illustration. So, here as you see, there are two gears as you can kind of see here, this is gear 1, gear 2, and they are moving in a direction. This moves in anti-clockwise sense, this is actually driven in the clockwise sense, and as a result of which the material which is inside this microchannel kind of gets pushed forward and flows in this direction. Okay. So, therefore, this is also used for cases where the flows are concerning a little bit high viscous material, high viscous fluids. Here is another illustration of a very interesting ferrofluidic magnetic micropump. Here you create a plug, okay, and this plug can be of a ferrofluidic nature. That means you have oil which is immersing some ferrous nanoparticles, okay, and it moves as a plug. Now, when you actually apply a permanent magnet in such a situation, there is always a tendency that as you move the magnet, the ferrofluidic plug also moves along with it, okay, and in that manner it kind of pushes the fluid past it, and thus a delta H difference can be created, which is supplied by this magnetic field onto this coupling ferrofluidic plug. So, there is another very interesting moving mechanism of moving fluids at the microscopic length scale, as you can see here in this particular illustration. Okay. The third kind of pump is really very interesting. It is the ferrofluidic micropumps, and you have to really consider in details the various stages from 1 to 5 of this particular pump and how it behaves. So, you have instead of one ferrofluidic plug, 2 plugs. Okay. Essentially, this particular illustration is one plug, and this here, as you see, is the second plug, and you have instead of one magnet, 2 magnets 1 and 2, which are placed on both ends, one towards the inside of the circle, another towards the outside of the circle. Let us say we call these 2 and 1 respectively. So, we move further the magnet 2 in the clockwise sense. Okay. So, as the magnet moves, it drives this ferromagnetic plug along with it, as you can see, and here it has kind of touched this particular system, and then it becomes one integral and blocks this port. Mind you, this is blocking this port. Okay. In the next illustration, as the magnet is further moved, so it changes position further and goes here. What happens is that this is a fixed magnet. As you see, this is a fixed magnet, it is not moving. The variable magnet moves the other portion of the plug away from this static plug here, which has been formulated. But what happens is that it creates a zone of low pressure here in this region, okay, as it does it. And as you know, fluid is capable of going into or rushing into the low pressure region. It kind of rushes into this low pressure region, and this magnet again comes back, and as it comes back, it pushes the whole column here, because this is a static magnet, it cannot go forward. So, as it pushes this thing, it pushes the whole column back into this, and so essentially the fluid transport is taking place from the second arm here, okay, as you are seeing. So, this is the second arm which causes the fluid transport to happen, and this is the first arm, which is the inlet to the micropump. Now, as you rotate this fast, the fluid kind of comes into every time as the magnet, as the ferrofluidic material joins here and then splits here, and then as it moves along, this whole other path of fluid is actually injected out, and that is how in the sequence of 5 steps you can get to realize a continuous flow micropumping system. This is again another very interesting example, osmotic micropumps. They happen especially because of membrane pressure. We have done this before. What osmosis really means, it is the diffusion of ions across a membrane, a semi-permeable membrane, with a concentration gradient across it. So, you have, let us say, salt solution on one end and plain water on another end. So, there is a tendency of the salts to diffuse away from the higher concentration side towards the lower concentration side, and this itself causes some kind of an osmotic pressure which can drive the fluids across this membrane as the ions cross over. Simply speaking, the ions do not have to move particularly on its own, okay, and essentially what happens is that it just drives the fluid along with it, and so therefore, if there is an ion movement, there is automatically a fluid movement as well. You just need to create a concentration gradient across the diffusing mechanisms. So, this kind of brings us to an end of these micro pumping devices, and we have kind of seen what microfluidics so far can do with respect to mixers, valves, pumps, and different kind of bioassays like the PCR microchip, whether it is space domain or time domain, so on and so forth. So we have done kind of a range of applications of microfluidics into biomems, which can serve various useful and important purposes. Now the only question which remains unaddressed so far is how do we really fabricate such devices using silicon processing. And as you know, as I have discussed before repeatedly, the focus of these biomems or in general MEMS is kind of developing novel and newer fabrication techniques of realizing these prototypes. And as we started with silicon and MEMS, and we discussed at towards the very beginning of this lecture, there was a general trend of following processes and steps which are normally used in the silicon industry, because the first material which came into the purview of MEMS was silicon. But as things moved along, there were polymer MEMS, there were carbon MEMS, there are basically biological devices or things made up of biological entities which would be serving as biomems devices, etc. And so therefore we can really study or begin this study of fabricating devices with alone doing in more details what we can do with silicon processes. So in a nutshell, the materials, again I would just like to use this slide from my other lectures before, that we can use silicon microelectronic materials, primarily glass quartz because of their optical transparency, and some polymers here like PDMS, PMMA. You have probably already seen part of this activity before, Teflon, and biological entities like cells, proteins, DNA, which gives novel frontiers in biomems. So let us talk about a little bit about crystal structures and how can we organizedly characterize silicon as. So if you consider this particular area here, it is essentially the transition from liquid to solid. So you have a liquid state underneath it, a solid state over it, and this is also the zone of fusion. So let us consider the properties here. Let us say that you have a temperature in the solid phase T2, liquid phase T1, and there is a flow of heat from the higher temperature towards the lower temperature. So if you actually consider Newton's law of cooling, what it states is that if you suppose have a certain sectional area here in a particular solid, let us say these are two fixed boundaries across which you are considering heat transfer, and you have this particular section across which you are considering what is the rate of heat flow. So essentially here let us say you have Q dot heat which is flowing across this boundary, and across this boundary Q dot x plus dx. So essentially it is a process dependent on the temperature gradient available across this. So if I have a temperature dt difference between these two surfaces, therefore the heat flux Q dot x is represented as minus k times A times of dt by dx. Okay, K is so called the thermal conductivity of the material, A is the area of heat flow, area of heat flux, okay, and which is perpendicular to this particular cross section, the cross sectional plane of this particular figure, and dt by dx is the temperature gradient which is available. So now you are seeing here that there is really a temperature gradient, and therefore there should be a heat flow. Let us say on this side, so you have this as the zone of fusion, you have a certain heat flow Q1x from the liquid into the zone of fusion, and on this side you have a certain heat flow Q2x based on the zone of fusion to the solid zone. And let us suppose that T1 is much greater than T2, because T1 of course being in the liquid state would have more temperature than that being in the solid state. So the direction of heat flow therefore, by using Newton's law of cooling, would be from T1 to T2, right, from the higher temperature to the lower temperature. And so let us actually write down the equation of such a flow. Okay, so let us suppose we have this solid emanating out from this small zone of fusion here, and here you have liquid state surrounding. So this is liquid, the solid silicon, this is zone of fusion. Okay, and essentially you have properties Ks as the conductivity of the solid phase, Kl as the conductivity of the liquid phase, and let us suppose that you have different or differential dt by dx. This let us consider as that in the liquid phase, and this let us consider as that in the solid phase. Okay. So, the total amount of heat flux across the zone of fusion would really be equal to minus Kl times A dt by dx in the liquid phase, right. The heat across into the zone of fusion minus of Ks solid phase times of A times of dt by dx in the solid phase. Okay. And that essentially is the total amount of heat which passes into the atmosphere or into the solid phase from the liquid phase. And if we consider dm by dt as the formulation of solid from liquid and L be the latent heat of formulation of or latent heat of change of state. So, therefore, this amount of heat needs to be lost from the liquid to achieve the solid. So, this amount of the heat is effectively the heat across the zone of fusion which leads to the formulation of solid silicon. Okay. So, considering that you have this L dm by dt which is the amount of heat required by the zone of fusion, and dm by dt is of course the rate of change of rate of formulation of mass, is actually equal to minus Kl A dt by dx at the liquid phase minus Ks A dt by dx in the solid phase. Okay. A is the cross sectional area of the zone of fusion and dt by dx is the thermal gradient in the n direction. Let me just write this down. So, A is the cross sectional area of the zone of fusion, okay, and dt by dx is the thermal gradient in n direction. Kl is the thermal conductivity of liquid, Ks is the thermal conductivity of solid. Now, having said that, we can really find out that Ks times of area A times of dt by ds dt by dx in the solid phase minus Kl A times of dt by dx in the liquid phase equal to L dm by dt. Dm can be substituted as the density of the solid silicon times of area of cross section of the particular solid that is formulated. We assume a uniform cross sectional area at least at the interface, times of dx, where dx is the differential of solid that is produced in time dt. Okay. That is what the whole idea is. So, this can be written as L rho A times of dx by dt. So, dx by dt essentially is nothing but the pull rate, the velocity of formation of solid silicon. Okay. That is what dx by dt would naturally mean. And if you assume the only situation where this dx by dt can be maximum would be the case when this here effectively is 0. Okay. Mathematically that is what it is. So, if at the most L rho A dx by dt max can be written as thermal conductivity of the solid times area of cross section times dt by dx of the solid phase. Okay. And essentially we can, so this is corresponding to Kl dt by dx of the liquid phase being equal to 0. What it means is that we assume only a one directional heat flux problem, or the heat flux is assumed only to flow in one direction from the liquid directly into the zone of fusion. There is no heat loss across the surroundings. So, whatever flow or whatever heat flows in is exactly whatever heat flows out. Okay. So, therefore, if we consider that to happen and we consider Kl A dt by dx is 0, then in that case the maximum velocity comes out to be Ks by L times rho dt by dx in the solid phase. So, essentially whatever the temperature gradient in the solid phase is from the zone of fusion onwards would determine multiplied by thermal conductivity of the solid by things like the latent heat of formation and the density of solid silicon. This would determine the maximum pull rate or the maximum velocity. Okay. So, that is essentially written as V max equals dx by dt equals k by rho L dt by dx. Okay. And so, in reality maximum pull rel is never used. As I told you before that the crystalline quality is a very sensitive function of the pull rate. So, the crystal quality really depends on pull rate. So, you really cannot go very high in terms of pull rate, otherwise there would be a set of point defects which can quickly escape and go into the solid material. However, too much gradient also may create large thermal stresses and thus dislocations, particularly in large diameter wafer. So, in a nutshell it is really the optimum best which can be derived experimentally as to what the pull rate would be in real terms. So, that is one method of how a certain direction or certain orientation, a prominence of one direction is used in silicon crystals. So, I would like to close this particular lecture here, as the time is almost over, but in the next lecture we will look at another method of formulation of silicon, followed by some of the more detailed processes of the MEMS industry which are borrowed from microelectronics. Thank you.